Hi there, everybody. Welcome to the online seminars for Specialist Mathematics Units 3 and 4 for the VCE Summer School 2023. My name is Sai Pemaraju, and I am one of the tutors at VCES 2023. And this year I'm focusing entirely on delivering these online seminars in both Spec Maths and Physics for you. So if you have any questions or concerns about the content of the seminar at all, of either subject, for those of you who are doing physics as well, please feel free to reach out to me on this email, student.unimelb.edu.au. But the topic of this seminar is not physics, obviously, it's Spec Maths. And the focus of this seminar in particular, this will be one of two seminars, is we'll focus on differential equations. And the reason I've chosen to focus on this is because a large portion of Unit 4 of the Spec course relies on differential equations and their applications to real-world problems, particularly those relating to motion of objects or fluid flowing into a tank. You see a whole range of applications. So for anyone who's interested in pursuing a career in physics or engineering, trust me, this is not the last differential equations course you will see. You will do these to death in later years. Okay, but that I'm not meaning to scare you here. So the agenda for today, what I had planned in the next sort of half hour, what I'd planned to cover in the next half an hour or so, is the following. Firstly, I'd like to introduce the idea of a differential equation, what it actually is, because that would help solving it. Okay, and then we'll move on to focusing on differential equations that are functions of the independent variable, following which we'll look at differential equations with functions of the dependent variable. And lastly, we will focus on the really important technique of solving differential equations, which is separation of variables. So this is a very important method of solving differential equations, and it's very important that we understand how it works, because a lot of the more advanced differential equations also rely on this method to being solved. Okay, without further ado, let's jump straight into the introduction to differential equations. So what is a differential equation? Funnily enough, it has a relatively simple definition. A differential equation is just an equation that contains derivatives of a particular function with respect to some variable. So for those of you who've done 1-2 methods, which I'm presuming all of you have, you may have seen equations that look like this before when you were covering anti-differentiation, for instance. The first example here is dy dx equals cos x. And you may have seen something like this when you were doing calculus in year 11. Another type of differential equation is this one. Dy dx is equal to y over 3y plus 4. See, you have a derivative. You have a derivative of some function with respect to some variable, and you have a right-hand side. You have a function on the right-hand side. So the first two examples here, the first two examples of these differential equations are what are called first order differential equations. And the reason why they're called first order is because you're only taking one derivative. There are no second derivatives involved in this. You're not differentiating the same function twice, say. The other difference between this first one and this second differential equation is the variable that's involved. So on the left, we have cos x. So our derivative with respect to x ends up being a function of x. Whereas in the second one, you have the derivative with respect to x being dependent on y, the function that we are interested in. We will see how to tackle each of these differential equations in the coming sections. Last but not least, we have d second y dx squared minus 4 dy dx equals 0. This is not a first order differential equation because we have a second derivative here. We're taking y, we're differentiating it twice with respect to x, and that's our second derivative. So this is what's called a second order differential equation. One thing I will suggest for those of you who may not be familiar with, who may not be comfortable with processes of differentiation and anti-differentiation, I would strongly recommend that you please familiarize yourself and get comfortable with these before jumping into this lesson, because a lot of the content in this lesson relies heavily on that. Back to what we were talking about before. Solving a differential equation means that we are trying to find the particular function or the relation that we have. So for instance, in this first one, we have dy dx equals cos x, and our end goal is to find out what y is. So what's y given? What's y equal to? Every time I pause here, I would strongly encourage you to pause the video, give it a crack on your own, give the problem a go at on your own, and then resume the video to have a look at the solution. So to find dy dx equals cos x, to find y in that case, you would need to anti-differentiate cos x with respect to x. And if you anti-differentiate cos x, you will get sine x plus some constant. Please do not forget your constant when you are anti-differentiating. So this is our solution to the differential equation. This is what y is. This is what's called a general solution. General because we don't exactly know what C is. C could be a whole bunch of different, C could take on a whole bunch of different values. We don't exactly know. And there's no way of working out what C is based on just the question based on just the information we're given in this question. To find out what the value of C is, you'll generally be required, generally more information will be required. So this is a general solution. So if a solution, so if you have a problem which gives you information to find the value of C, and you find a solution to that, that's what's called a particular solution. Particular solutions are when you know the value of C. Okay. So one thing we can do, rather than explicitly solve a differential equation, is to verify that a certain function satisfies a particular differential equation. So that's what that is. So let's see how this is done. And here I have a worked example. One thing I will add is, one thing I'll emphasize once again is if you have, if we come across a worked example, I would strongly encourage you to pause the video, give it a try on your own first, and then resume the video to see how the solution is arrived at. Okay, so firstly, we want to verify that y equals ae to the power of x minus 1 satisfies that differential equation dy dx equals x plus y. Okay, so we actually don't have to do any solving. All it says is to verify. We've been given an answer and we want to see that it satisfies a given differential equation. So let's do that. The way we do that is we compute the left-hand side of the equation first, and then we compute the right-hand side of the equation, and then hopefully if this claim is true, then if the claim made in the question is true, then the differential equation, the left-hand side must equal the right-hand side. So let's quickly go ahead and do that. Let's compute the left-hand side. So the left-hand side is just taking the derivative of y with respect to x, where y is this function here, ae to the power of x minus 1. So quickly differentiating that gives us a e to the x minus 1. On the right-hand side, what we have is x plus y. That's what we have. Remember, y is this function here. So that's not a question. It's the y is given by this function over here. Okay, so x plus y is x plus a e to the x minus 1. Now, with some, if you look closely, you will see that this x and that x disappear because they cancel out, and we are left with a e to the power of x minus 1. But hey, look, our left-hand side equals our right-hand side, a e to the x minus 1, a e to the x minus 1. Hence, our left-hand side equals our right-hand side, and so we have verified it. Yay, we've made it. Fantastic. So we have, we know how to verify that a given differential equation is satisfied by a particular function. Cool. Relatively straightforward, I hope. If you have any questions regarding this or anything else that comes up, please feel free to reach out to me on this email once again. Okay, let's move on. Let's move on to differential equations with functions of the independent variable. And actually, for those of you who may have done anti-differentiation in methods, which I'm presuming many, if not all of you have, this is something you may have seen already. So the independent variable, what do I mean when I say the independent variable? The independent variable is the one that we change to see a difference in the other quantity. For those of you who are doing sciences, you may know this from experiments. Okay, so in this case, in general, for a function, we change the value of x to see the change in y. That's why it's called the independent variable. X is our independent variable. So we're looking to solve equations that look like this. So where the derivative depends on x, where the derivative is actually a function of x, or the second derivative is a function of x. And the way we do that is to simply anti-differentiate with respect to x, and we get some sort of a solution there. So here we want to find, in this worked example, we want to find the general solution of dy dx equals e to the power of 2x, and the particular solution where y of 0 is equal to 3. So let's just focus on the general solution for now. General solution. And please feel free to pause the video and have a crack at this question on your own if you feel like jumping ahead, and then resume the video once again to see the solution. Okay, so we have dy dx equals e to the power of 2x. So our general solution, so if we have dy dx equals e to the power of 2x, then our y is given by the antiderivative of e to the power of 2x with respect to x. So what we end up with here is a half e to the power of 2x plus c, because we are looking at a general solution where c is a real number. Please do not forget to specify what c is in an exam or an assessment, because if you just introduce a constant c without telling people what it is, that causes a lot of confusion. Okay, so that's the general solution. What about the particular solution? The particular solution isn't too difficult from here. All we have to do is to substitute our initial condition, the condition that we've been given in the question, which says that when x is equal to 0, y is equal to 3. So x equals 0 implies that y equals 3. In that case, what we have is, if we sub in our conditions, we have 3 equals a half e to the 2 times 0 plus c. So then we have a half plus c equals 3. e to the power of 0 is 1, so a half times 1 is just a half. So a half plus c equals 3, and this means that c is equal to 5 over 2. So 3 minus a half is 5 over 2. So our particular solution is y equals a half e to the 2x plus 5 over 2. If you really want, you can take out a common factor of a half and make it look better, but I'm not going to bother because we've arrived at our solution already. This is our solution. So that's how we approach solving differential equations that are functions of the independent variable. Now let's move on to differential equations with functions of the dependent variable. So the dependent variable is the one that we measure in scientific experiments. And in this case, in the case of functions, we generally want to find the value of y, so the y value of something. And so these kind of differential equations, their derivative with respect to x depends on y, actually. So the dy dx is a function of y. This is what this line is saying. In this case, what we do is we use an identity. We say that dx dy, take the derivative of x with respect to y. We assert that that is equal to 1 over dy dx. Now, this is not true for all functions, but in all the functions that you see here, in this course, it will be true. So dx dy is given by 1 over g of y, because dy dx is g of y. And so once we get x in terms of y, the way that we get x in terms of y is we anti-differentiate much like we did before. Once we anti-differentiate, here's where the difference comes in from the previous type of question. Once we anti-differentiate, we will solve for y. We will invert that expression to get y as a function of x. That sounds like a lot of words. Let's jump into an example to see how this exactly works. So in this example, we want to find the general solution of dy dx equals e to the 2y. So we have a derivative with respect to x on the left-hand side, and that is equal to e to the power of 2y on the right-hand side. So using our identity from up here, we know that dx dy is 1 over dy dx. So let's write that down. So dx is 1 over dy dx. And so that is equal to 1 over e to the 2y. For those of you who are eagle-eyed and are familiar with your index laws, you will notice that this is the same as e to the minus 2y. So what we have is dy dx equals, dx dy, dx dy equals e to the minus 2y. Once we have, now we have x, now we have a derivative with respect to y on the left, and we have a function of y on the right. So what we can do now is we can just simply anti-differentiate this to find x in terms of y. X equals the antiderivative of e to the minus 2y with respect to y. Okay, so what that gives us is the following. That gives us minus a half e to the minus 2y plus c, where c is just some constant again. Let me just move that here. C is a real constant. Okay, so we have x equals minus a half e to the minus 2y plus c. I've specified what c is. I'm not going to do it here again. So let's rearrange this expression for y. First, we move the c to both sides. We get x minus c equals minus a half e to the minus 2y. Then we do, we multiply both sides by 2, by negative 2 rather, minus 2x minus c equals e to the minus 2y. To undo that, to undo the exponential, we take the log base e of both sides. So log base e of minus 2x minus c is minus 2y. And then finally, just to get rid of the -2, we divide both sides by 2. We get minus a half log base e of minus 2x minus c. And there's our answer. We have y as a function of x, even though our original derivative ended up being a function of y. We end up with y as a function of x always. There you go. So this is how you deal with DE's differential equations with that are functions of the dependent variable. Oh, my work has bled over into the next section, so I will move that up here. Okay, cool. All good. The last thing I want to focus on in this seminar is the most important method of separation of variables. Here, we'll consider only first order differential equations, but this method is generally applicable to a whole bunch of second order differential equations as well. So a first order differential equation is defined as being separable when it can be written as follows. So when it can be written as a function of x times another function of y. So if you can split up the components of the function into a function of x and a function of y. The way we solve this is we move all the x-dependent terms to one side of the equation, and we move the y terms to the other side of the equation, and then anti-differentiate both sides. Lastly, to complete the process, we solve for y as a function of x. So that's what we do. Let's see how this works in practice. What we have here is we want to solve the differential equation. This is actually a VCAR exam question, by the way. We want to solve this differential equation, which looks like this. We want to solve dy dx equals minus x times the square root of 4 minus y squared, given that y of 2 equals 0. Okay, so we have to find a particular solution in this case. Let's start off by finding the general one. So we have dy dx equals minus x root 4 minus y squared. Okay, so let's move all the x-dependent terms to one side. So the x-dependent terms are the x and also this dx, actually. Our y-dependent terms are root 4 minus y squared, as well as the dy. Now, I'd refer to dy dx as terms of an expression, but strictly speaking, they're not. In this case, we can think of them as that, but they strictly are not considered as terms of the expression. So if we move all the x-related things to one side, we have minus 1 over root 4 minus y squared dy. This is when we moved all the y terms to the left and the x terms to the right. We get x dx. Our next step is to anti-differentiate both sides. So let's do that. Anti-differentiate both sides with respect to their variables. And let's evaluate both of these antiderivatives. The right-hand side is relatively straightforward, right? It's the antiderivative of x, which is x squared on 2. I'll say c1 plus c1. c1 is the constant. And on the left-hand side, well, how do I do that antiderivative? I can't remember how to do this one. Aha, wait, let me have a look at my formula sheet, which I have pasted here. So we had minus 1 over the square root of 4 minus y squared. That looks very much like this one here, where our a is a squared is actually given by 4. So a is equal to 2. So what that says is that antiderivative is equal to the arc cosine of x over a. So in our case, that'd be arc cos of x on 2. Plus, we need another constant, C2. And let's specify that C1, C2 are both real numbers. And let's, so what I'm going to do now is do something sneaky. Let's move all the constants to one side. X on 2 equals x squared on 2 plus C1 minus C2. And let me call this a different constant, D. So the difference of two constants is another constant. I'll just combine those two and call it something new, just so that I don't have to deal with C's all over the place. So this is then cos inverse of x on 2 equals x squared on 2 plus d, where d is equal to C1 minus C2. Okay, we found the general, oh, whoops, all these x's should be y's. They're on the left, y on 2, y on 2, y on 2. Y on 2, y on 2, y on 2. Okay. So now we want to find y as a function of x. So let's start undoing this expression and trying to find y. So to undo an arc cos, we take the cos of both sides. So cos of x squared on 2 plus d equals y on 2. Then solving for y, we get cos of, so 2 times the cos of x squared on 2 plus d, and that's our general solution. For our particular solution, what we do is we plug in the initial condition. So y of 2 equals 0. So when x is equal to 2, y is equal to 0. Then we have y equals 2 cos, so 2 squared on 2 is just 2. So then we have cos of 2 plus d equals 0. So then 2 plus d is pi on 2, right? Because cos of pi over 2 is 0. And then d is equal to pi over 2 minus 2, which is pi minus 4 on 2. Okay, so putting everything together, we have y equals 2 cos 2 plus pi minus 4 on 2. And that's our solution. Okay, so I have just verified that that is, it's not 2 cos 2 plus pi over 4. Let me just rewrite that again. Equal to 2 cos, what did we have? X squared on 2 plus pi on 2 minus 2. I've just rewritten this as pi on 2 minus 2. And there's our solution. Cool. So that is how we approach a a problem that involves separation of variables, and this is a really, really important method of solving differential equations. And so it's really, really important that you familiarize yourself with it, because there are a lot of exam questions based on it, as well as for people who are considering doing higher level maths. This is a very, very important technique. Okay, so that concludes the first seminar, focusing entirely on differential equations. Here today, we went through an introduction. Once again, just to recap, we went through an introduction as to what DEs are. We went through functions of independent variables and how to solve them, as well as dependent variables. And we just concluded on the very important method of separation of variables. So that's all I have for this video. If you do have any questions or comments or concerns, please feel free to reach out to me on this email here. Thank you so much for tuning in, and I hope to see you soon in the next one. Bye-bye.